For this example, let's assume that we already have done the work to get the transfer function and to identify our system parameters by getting it into its standard form. So we're going to be given that we already know the natural frequency is going to be 25 radians per second. And we have an underdamped system with a zeta value of 0.15. We're told that our A value is 8 and our B value is 3. And for later comparison, we can reconstruct what this transfer function would be so that we can plot it in MATLAB and compare it to our sketch. Because again, we know our standard form is going to be A omega n squared over S squared plus 2 zeta omega n times S plus 25 squared. And so this will, when we put this into MATLAB, we should get the exact same, it'll match the sketch that we make on the board here. All right, so we have all this done, we have our 4 system parameters, so let's see how we can get a little bit better sketch than the previous example, because now we're going to take into account how the oscillations are going to attenuate, and we're going to get the proper periodicity as we make our sketch. Again, we can look at our zeta value of 0.15, we know that we have an underdamped system in place. So based on what we have here so far, let's find some of the response values that we're going to find. So one, we can look at the damped frequency because we know that all of the oscillations in our damped system are going to be oscillating at the damped frequency, which is different than the natural frequency, but it's calculated by using the natural frequency. Right, so it's going to be the natural frequency times the square root of 1 minus zeta squared, only if we have an underdamped system. So that's 25 times the square root of 1 minus 0.15 squared. So we come up with a damped frequency, 24.7 radians per second. Yeah, so the reason we want this is we're going to be able to use this to find the period of our oscillation, which is related to our peak time, because the peak time is going to be 1/2 period of oscillation. Okay, so peak time is going to be pi over omega d, which we just found. So it's pi over 24.7 is going to give us 0.127 seconds. And just our general period is just 2 pi over omega d, so it's twice our peak time, or our peak time is half of our period. So that comes out to 0.254 seconds. Right, so we'll use this for the timing when we make our sketch. Right now, we have a couple of different options of how can we find, for the sketch purposes, I want to find peaks, I want to find valleys, so I can see how this signal is kind of closing in on that steady state value. So one thing is, let's find the steady state value. And we know that that's going to be A times B, so 8 times 3, it's going to be 24 at steady state. And what we can do also, again, there's different ways we could approach this. I'm going to find the max overshoot so that we can find what the peak value is. But from different equations, we would find this out automatically. And we'll see that as we get into the sketch. So the max overshoot, we're going to have E, as we've seen before, to the negative pi zeta power, or negative pi zeta over root 1 minus zeta squared. So the max overshoot is 0.621. Again, I'll reiterate, the max overshoot is not the value of y at its maximum. This is a ratio of the maximum value to the steady state value. So this says that the maximum value will be 62% larger than the steady state value. And that will be reflected in our plot. All right, so let's start to get some plot points down as we go. So this will be our time. This will be our, I'll just call it again, y of t here for our response. So steady state value is at 24. And what I can do with my time is I'll just split it up into periods. So this will be a full period. So that will be 0.254 seconds. So about half of that will be my peak time. And trying to be to scale as much as I can. 2 periods, 3 periods, And we'll have some in-betweens as well because we're going to go from peak to valley as we go through this. So we know when the peaks and the valleys are going to occur because it's going to be peak, valley, peak, valley, peak, valley. Now we need to know what the values are going to be at those peaks and valleys. So as a starting point, the peak time tells us when the largest value is going to be. And one thing we can do is look at the max overshoot here, and we can use that to compute what is the peak value going to be. Now I'm going to call that my y0 value. So I can do, one thing is 1 plus MP, so that will be 1.621, so that's basically saying what's 162% of my steady state value, which we know is 24. Okay, so calculating that out, 38.9. Okay, so let's say we're somewhere about there, at 38.9. Now what I can look at is I know I'll have a valley, then a peak, valley, valley. I'll just do a couple of oscillations here for my sketch. So the next peak will be on 1.5 periods, or 3/2 t. This is 1/2 of t. All right, so I can compute what that is using the equations that we have previously. So I know that I can take the steady state value, and I can multiply that by 1 plus e to the negative zeta omega n t power. And this, basically what this describes is the envelope, which I'll sketch in a minute here, the envelope of the oscillation. So what is the bounding envelope of oscillations that we're going to have? So this does not tell us what the value of the function is at all times. This is only the envelope. However, if we plug in periods and half periods here, we know that the envelope coincides with our oscillations at those exact times. So what I can do is if I call this, let's say this is my y0, this is steady state. And move this over a little bit. If I put in the time here of 3/2 of a period, that's going to tell me what really the second peak is. I'll call that the y1 value. So the y1 value, if I put in the value of zeta, if I put in omega n, and if I put in 3/2 times 0.254, I am going to get 29.7. And yeah, I'll just call that y1. So that will be my second peak. Now again, there's other ways we can do this. We can do a peak-to-peak difference, which is another equation that we saw on the slides. But this one I think works a little bit easier. But again, it only works at half periods and full periods of oscillation. And if we sketch this out, which we'll do later, we'll see what these curves look like, because we can do plus or minus this, or 1 plus or minus that exponent to get those bounding braces. Right? And then we can do another one. I can calculate y2, and for this one, zeta and omega n are the same, but now I want to know the peak at over here, which will be 5/2 t, or 2.5 t, will be my third peak. So that's what I'm computing here. So I put in 5/2 t here, and I get that y2, 26.2. And the peak should be getting closer and closer to the steady state, because as time goes to infinity, this exponential term is going to go to 0. So we have 1 plus 0. So it'll get very, very close to steady state as that time goes forward. And bringing that out, that's what I'm calling the y2 of 26.2. Right, so similarly, we can find valleys here. I'm not going to go through all of the steps, but it's exactly what I'm doing here. The valley is going to occur at 1 minus this exponential. And the valleys are occurring on the whole periods, on t and 2t. So if I want to know this first valley here, I'm going to use this equation, but I'm going to say it's 1 minus now. So I'll do plus minus. So minus tells me where the valleys are. So putting in my zeta, my omega n, and 0.254, and putting into this equation, I'm going to get my first valley. It will be 14.7. And I will do one more, I think. Oops, I put this in the wrong spot. That goes there. This one's going to be a valley because it's a whole period. That's going to be at 20.4. So again, it gets closer and closer to my steady state value. Okay, so I have a couple of plot points here. Peaks and valleys I use now that I know the period and the half periods, putting into here. Now I can start to put this together. I know I'm starting at 0, so I want to hit my first peak, my first valley, peak, valley, peak. And again, it gets closer and closer to that steady state value. And what we will see when we plot this in MATLAB is that if we plot out this entire function, the plus and then the minus, that gives us these bounding curves. So sketching them really roughly like that, these decaying curves are the envelope in which our oscillations are all going to occur. So now through our sketch, completely analytically right now, we have peaks and valleys. We did it for a couple of periods. We know the period of oscillation, and we have, at least visually here, that bounding envelope. So now what we can do is compare it to when we put all the way back in this step, this function into MATLAB, and now numerically we can simulate what's going to be happening. Now we can compare our sketch to the numeric results from MATLAB. So taking this now into MATLAB, I'm putting in the givens, the damping ratio, the natural frequency were given to us, that value of A, and we calculate from that our damped frequency and our period. So all of that's going in. The values we calculated for our max peak, the first valley, the second peak, and the second valley, I'm also putting in. All right, so on the numerical side, here in line 31, I'm defining g, the transfer function, as I showed earlier, using the given information. So I was told the value of a was 8, and I know that the numerator of my transfer function is a times omega n squared. And then my denominator, when it's in the standard form, should be s squared, then 2 zeta omega n s, and then omega n squared as the constant. So that's why I'm entering into 31, reconstructing the transfer function from the given parameters that were provided to us. And in this case, I'm giving it a step input, a 3-unit step input in line 32, so 3 times g, and I'm going to plot this for only 1.4 seconds. And we see that the resolution is pretty high that I'm doing this at. And then I'm going to plot it. And what we're also going to see are these bounding envelopes I was referring to earlier. That is our steady state value times the 1 plus that exponential and 1 minus that exponential. And that's going to be the envelope above and below our oscillating function that it can't go outside of. So let's see what happens when we plot this. In the command window, it's showing the times of the half period and the full period. You see in the plot here, I'm only plotting it for, I'm not showing where the periods or half periods are. I'm just doing a standard time of a spacing of 0.2. But when we zoom in, we're going to be able to see those times. All right, so if I go in here and I see where the peaks are that we have numerically, they will match what we got in the sketch, at least pretty close. All right, so we see here our maximum value, or that first peak, happens has a value of 38.9, and it happens at 0.127 seconds. So pretty close to what we got analytically, pretty close to what we see in the sketch. If we see the first valley, this is going to occur at that at one time period, so 0.256 seconds, and as we have on our sketch, as a value of 14.82. And we can check all of these, and we're going to see that they're all going to agree pretty close to what we got in our sketch. Now, in blue, again, this is the actual plot. This is what we sketched. These dashed lines above and below are that bounding envelope that we're plotting, that exponential function. And we see that the envelope matches where the peaks are from above, and from below it matches where all of those valleys are. So it only agrees exactly at the peaks and the valleys, and otherwise it shows that our oscillations are never going outside those bounds. Also, this is showing where that kind of 5% settling time, 10% settling time is coming from, because that bounding dashed line we can see where does it first enter plus or minus 10% of the steady state value. Well, we know that since it's decaying, it never goes outside of that.